more examples of balancing chemical equations. These are a little bit more complicated than the first one that we did, where everything was just a coefficient of 1. But we're going to follow the same process. So we will split this into the reactant side, the product side. Again, you don't have to draw that dotted line. I just think it's a good visual so that you keep everything on the correct side. So reactant side, product side. And we're just looking at this reaction right now. So aluminum bromide plus potassium yields potassium bromide plus aluminum. That's how we would say that in words. So I'm going to go ahead and do my atom inventory. I'll write out the atoms that I have on the reactant side, and then remember that it's helpful to write them in the same order on the other side, even if they don't appear in the same order up here. Like potassium's first over here instead of aluminum, but this way I can just easily look across and see if I have the same number of aluminum atoms. So on the left, I have 1 aluminum atom, I have 3 bromine atoms, and I have 1 potassium atom. On the right, for the products, I have 1 aluminum, 1 bromine, and also 1 potassium. So I'm going to start looking, and I see that the aluminums, I have 1 and 1. So they are currently balanced, so I don't need to do anything to the compounds with aluminum in them. But then I come to bromine, and I see that there are 3 bromines on the left and only 1 on the right. So I need to have the same number on each side, because right now I destroyed matter. I had 3, now I only have 1. That's not possible. So in order to fix that, I'm going to look for where bromine is. It's in the potassium bromide compound. If I put a coefficient of 3 in front of that, now I have not 1, but I have 3 times 1, 3 bromine atoms. Now, I can't just put a subscript of 3 there next to the bromine, because that would not be potassium bromide anymore. Remember that this is an ionic compound. It's based on charges, and so K plus 1, Br minus 1 together is just K1, Br1. It can't be KBr3. So the way to make there be 3 bromine atoms is to have 3 formula units of potassium bromide. Now you might be saying to yourself, well, wait, now you have 3 potassiums also. You're right, I do. So I need to change that to a 3 right there, which means before my potassiums were balanced. I had 1 and 1, but now I have 1 and 3. So they're not balanced anymore, but that's okay. I can apply the same thing I just did on the other side to this side. So I have 3 potassiums on the products. I need to have 3 on the reactants. Well, here's potassium. If I put a 3 in front of it, now I have 3 potassiums on this side, on the reactant side, as well as on the product side. So now I'm going to look across. Aluminum is 1 and 1, bromine 3 and 3, potassium 3 and 3. Everything is balanced, so what do I fill these 2 in with? Yep, 1s. Remember, they don't have to be written, but I suggest you write them, at least in the beginning, so that you know that there is something there, and you see that we have now completed balancing this reaction. Now let's look at this next one. All right, so again, let's split this in half. All right, and I have potassium chlorate yields potassium chloride and oxygen. Remember, oxygen is a diatomic, so that is just elemental oxygen, O2. So K, Cl, and O, write them, oops, I didn't go far enough there. K, Cl, and O. All right, on the left, I have 1 potassium, 1 chloride, and I have 3 oxygens. On the right, I have 1 potassium, 1 chlorine, and 2 oxygens. Okay, so potassium, already balanced. Chlorine, already balanced. Oxygen, 3 and 2. So it's not as simple this time. I can't just multiply 2 by something and get 3, and vice versa. I can't just multiply 3 by something. Well, I can't multiply it by a whole number, which your coefficients have to be whole numbers. So I cannot multiply this by a whole number and get a 2. When this occurs, the best course of action is to multiply them by each other. So watch what I mean. I'm going to multiply this by the amount of oxygens I have on the other side. If I multiply that by 2, it means I'm putting a coefficient of 2 in front of the whole thing. Now I have 6 oxygens. It also changed my amount of potassium and chlorine. I now have 2 of each of those. Make sure you keep up with your counts as you go, or you might forget something and get confused and not be able to finish the problem. So I multiplied this one by the number I had on the other side. Now I'm going to do the same thing here. So I'm going to multiply this 2 by 3. That's how many I had before on the other side. If I put a 3 in front of there, 3 times 2, I get 6. So now my oxygens are balanced. Wasn't so bad after all, right? Now I need to take care of the potassiums and the chlorines. So I have 2 of each on the left, and I only have 1 of each on the right. Well, thankfully, they're in a compound together. So if I put a coefficient of 2 in front of that compound, I now have 2 potassiums and 2 chlorine atoms. So 2, 2, 2, 2, 6, 6. Everything is balanced. And my coefficients are 2, 2, and 3. All right, this last one is a combustion reaction. We did not classify these two, but this was a single replacement reaction. This one is a decomposition reaction. And then we're dealing with a combustion reaction now. Combustion reactions are typically the most difficult to balance. Some are easier than others, but there's a few things that you need to remember from the balancing rules that were in your notes when it comes to balancing combustion reactions. And the biggest thing is to save your oxygens for very, very last to balance and your hydrogens for second to last. So that just leaves us with trying to balance carbon first. But definitely save oxygens for the last thing because they are usually going to be the most difficult in any reaction, but especially in a combustion reaction. So atom inventory first. We always start the same way. All right, on the left, 3 carbons, 8 hydrogens, 2 oxygens. On the right, the product side, 1 carbon, 2 hydrogens. Be careful counting your oxygens because I have 2 here and I have 1 here. So 3 total. All right, let's start balancing. First thing I see is that carbon is unbalanced, plus I don't want to do hydrogen and oxygen yet anyways. So carbon, I have 3 on the left and only 1 on the right. So if I put a coefficient of 3 in front of that carbon dioxide molecule, then now I have 3 carbons. But I also changed my amount of oxygens by doing that, since that molecule has both carbon and oxygen. So now I have 3 times 2, 6 oxygens, plus this one, don't forget about that guy, so that is 7 oxygens. Next thing, my carbons are balanced, so now I'm going to go to hydrogen and try to balance out hydrogen. On the left, I have 8 hydrogens. On the right, I only have 2. What should I multiply 2 by in order to have 8? Yes, if you said 4, you are correct. If I put a 4 in front of H2O, I now have 8 hydrogens. But now I need to recount my oxygens because I've now changed them again. So I still have 3 times 2 is 6 over here, but now I have 4 times 1 is 4, so I have 6 plus 4 oxygens, which is 10. Make sure you always recount them completely. It's very common that people like to just add this 4 to the 7, and that would not be correct because one of those was already accounted for before. So we actually only gained 3 by putting a 4 right there. So just make sure you recount, and that's the safe way to do it. Carbon is balanced, hydrogen is balanced. The only thing not balanced is oxygen. We have 2 on the left and 10 on the right. Thankfully, this is an even number, so I can multiply 2 by something to get 10. And that something is a 5. So if I multiply this by 5, I get 10 oxygens. Now, everything is balanced, so my final step is to fill in any blanks with a 1. And so that is the balanced equation for that combustion reaction.